For this method, we need to choose at least 4 points nearest to V equals to 5 volt. Next, we need to write the formula to find the first order of Lagrangian. Next, we just need to plug in the value to get the first order of Lagrangian value, which is equals to 4.05 milliampere. Next, we need to find the second order of Lagrangian and plug into the formula, and we get the value of 4.0125 milliampere. Repeat the same step to find the third order of Lagrangian and plug all the values into the formula, and we will get the same value of 4.0125 milliampere. Same for Newton's divided difference method, we need to choose points that are nearest to V equals to 5 volt. And firstly, we need to find the first order of Newton's divided difference. Next, find the second order difference and third order difference and plug all the values into the formula. Next, we need to plug in all the values that we get in the general form of Newton's divided difference formula. And lastly, we will get the answer of 4.0125 milliampere. To conclude, both methods give exactly the same result, which is 4.0125 milliampere at V equals to 5 volt. This confirms that for a given set of points and interpolation order, Lagrange and Newton's method are mathematically equivalent. Using a third-degree polynomial with 4 nearby points provided a smooth and accurate estimate at 5 volt.
For question number 2, the first method is trapezoidal rule. The formula is E is equal to h over 2 times fx0 plus 2fx1 plus 2fx2 plus 2fx3 plus 2fx4 plus fx5, and h is equal to b minus a over n. Given data from question 1, find the PV0, PV1, PV2, PV3, PV4, and PV5. After we get all the value for our P, plug in all the value that we get into the formula and calculate the energy stored in the capacitor to be 271 millijoules. For the second method, Gauss-Legendre method, the formula is P minus A over 2 times W1fx1 plus W2fx2. And the weights are W1 equal to W2, which is 1, and the roots are Z1 is equal to negative 1 over Z3 and Z2 is 1 over Z3. Next, calculate the value for V1 and V2 to be 2.113 and the V2 is 7.886 volt. By using the data from question 1, find the value for I1 using the linear interpolation method, and then we get I1 as 1.596 milliampere. And for I2 using the same linear interpolation method, we get as I2 is equal to 6.214 milliampere. And then after we calculate the value for I1 and I2, calculate the value for fx1 and fx2 using the formula, and we get fx1 as 3.37 milliwatt and fx2 is 49 milliwatt. After we get the value for the fx1 and fx2, put it in the formula given, and then we get energy stored to be 261.85 millijoules. For comparison, the first method is trapezoidal rule. The energy stored is 271 millijoules. The method is simple and easy to handle for evenly spaced data. And the second method is Gauss-Legendre. The energy stored is 261.85 millijoules. This method is more accurate and have a very good approximation. For conclusion, both methods give a very close answer to each other, but Gauss-Legendre gives more accurate and precise answer.
Question 3. Given dV over dt plus V over RC equal to 0. When t equal to 0 second, V is 10 volt. With R equal to 10 k ohm, C equal to 100 microfarad, find V when t equal to 1 second using two different methods for ODE when the step size is 0.1. compare your result and conclude your finding. Our first step is rearrange the equation. And then we will find dv over dt equal to negative v. Our first method is Euler's method. This is the formula for Euler's method. And then from the formula, we just need to insert the value of h, and then we will find 0.9 Vn. Here is the step-by-step table for Euler's method with step size 0.1. When t equal to 1, we will find v equal to 3.487. For the second method, we will use Hund's method or second order Runge-Kutta. This is the formula for Hund's method. Here is the step-by-step table for Hund's method with step size 0.1. We find that when t equal to 1, V is equal to 3.686 volt. This result is very close to the exact value, 3.678, showing that Hund's method is significantly more accurate than Euler's method. To conclude, Hund's method is significantly accurate than Euler's method because it improves the estimate of each step, which can reduce the overall error. Therefore, Hund's method provides of the true solution.